Hey, welcome back to Mr. PL's with Precal. This is Unit 1, Topic 1, Lesson number 9, and we are dealing with inverses, and we're going to start off with a warm-up that you should have done in Algebra 1, and Algebra 2. So what I'm going to do is I'm going to list all the order of all the operations in this function, negative 3x squared plus 7 divided by 2. First thing you would have to do is you have to do the x squared. So squared comes first, and then you're multiplying by negative 3, and then you would have to add 7. This is if you know what x is, and then the last step you would have to divide by 2. So in the inverse function, you know it's going to be the exact same steps, but it's going to be the opposite step, and it's going to be in the opposite order. So the inverse of divide by 2 would be times 2, and then it would be minus 7, and then it would be divide by negative 3, and then instead of squaring it was going to be square root. So I'm going to build the new function, so f inverse x, using the inverse order. So you multiply the number times 2, so that's 2 times x, and then you subtract 7, and then you divide that by negative 3, and then you do the square root of all of it, and there you go, you've got yourself the inverse function of the given original function. Alright, so that's a good warm-up for what we're going to be doing here in a second. So what about graphs of the inverse functions? The graphs of the inverse functions are blank over blank. So in this case, you'll notice that the inverse functions are always reflections over the y equals x line. So this line right here represents y equals x, and you'll see that this graph is a perfect reflection over that green line. Same with this. This purple function is a perfect reflection over this red line. Which of the three functions does not have an inverse function and why? And the one that doesn't have an inverse function is C, because when you reflect this blue parabola over the green dotted line, this red line is no longer going to be a function. How can you tell from the original function's graph that the inverse will be a function? So if the original function passes the the horizontal line test, then you know its inverse is going to be a function. In other words, if this red line is the original and you draw a horizontal line anywhere, you should never be able to hit that function more than once, no matter what location it is. Even if you hit it right here where it's curving, you're only going to hit the red line once. And the reason that is because when you reflect it, it's going to become a vertical line, and a vertical line test is how you prove whether or not something is a function or not. What do you know about the coordinates of the function and its inverse? What we do know is that the xy is going to turn into yx. So it's always the exact same points, only switched on two functions that are inverses. Is the inverse of this relation a function? Why or why not? So it is a function when you look at the first one, because it does pass the horizontal line test. This one is not going to be a function. So if you took this and you reflected over the y equals x, it's going to end up being like this, which is not a function. And the reason I know is because it hits once, twice, 3 times, 4 times. It hits multiple times. So it looks kind of like a cosine function, and it's going to hit multiple times if you draw a horizontal line. This one looks like it's going to pass the horizontal test, but it doesn't right here. In fact, if you draw a horizontal line right there, it hits multiple times, 1, 2, 3, 4 times. So this is not going to create a function when you do the inverse. What does the inverse function do? So let's take a look at the equation first. So the inverse function, as I had mentioned before, so the inverse is always just going to be the x and the y switched. So let's look at this equation first. So the inverse of fx minus 7. So the inverse, as we had talked about before, is just the same operations in the opposite order. The opposite operations in the opposite order. So instead of multiply by 5, then minus 7, it's going to be add 7. So that's x plus 7, and then divide by 5 instead of multiply by 5. So we know this is the inverse of this. So try this. Pick a value of x, evaluate it, and then put that value into the inverse. What should you get? Well, if I pick a number, it doesn't even matter what the number is. I'm going to pick the number 2. So 5 times 2 minus 7. So this is f of x. 5 times 2 is 10. 10 minus 7 is 3. And then I'm going to take that answer. I'm going to plug it into my inverse function. So 3 plus 7 is 10. Divided by 5 is 2. Now, it should not surprise you that I'm getting the same number at the end as I started with in the beginning. And that'll always happen, no matter if you pick 2 or any other number. So pick a value for x and put it in for, okay, so if I take a number and I put it in for this function, and then I take that answer and put it in for this x, then I should get the exact same answer I started with in this function as well. So in other words, f of negative 1x, f of f inverse x is going to be equal to x. You're always going to get the same x that you chose to put in the first time. And if you do the exact same for the opposite, which is the inverse of f of x, you'll also get x. So once again, whatever you put in the first time, and then you take that answer, plug it into the other function, you're going to end up getting whatever you chose for x to begin with. Let's look at this graphically. So f inverse of f of 2. So first thing I'm going to do is find what f of 2 is. So f of 2 is 0. If I put 0 in for the inverse, I get 2. So the answer is 2. So that makes sense because this number and this number are exactly going to be the same. So f inverse of 5, so 5, 3. So if I put 3 in for 5, there you go. You get 5 again. So exactly the same. So we can say that the graph of the inverse is composed with its inverse is the line y equals x. A function is 1 to 1. So these functions are 1 to 1 when they're inverses of each other. They're only if, this is basically what I had already been stating before, if, f of g of x, so if you say the inverse is g of x, is going to be equal to x, and g of f of x has to also equal x. So therefore, every x in the domain of G and every x in the domain of F. All right, so the original inverse table doesn't work for all equations. Okay, so the inverse table is not going to always work, especially when you have equations like this when you have x over x. So what you'll do in these special cases is you're going to set f of x equal to y, so make it y equals x plus 1 over x. Then I'm going to switch the x and the y's. So I'm going to put x in the y spots and y in the x spots. Okay, next thing I want to do is I want to solve for y. So I'm going to move this y by multiplying both sides by y. So that gives me xy equals y plus 1 because these y's canceled. Next thing I'm going to do is subtract y from both sides. So I now have xy minus y equals 1. My next step is to factor out the y. So this becomes y times x minus 1 equals 1. And the last thing I'm going to do is divide both sides by x minus 1. And I got y equals 1 over x minus 1. And there you go. You have the inverse of the original. So this is the f inverse x equals 1 over x minus 1. The inverse of this original function. And I think that's where I'm going to stop it right there. Those are just practice problems doing the exact same thing. Thanks again for watching, and have a great day.